Okay, so before we move on to specific distributions, discrete distributions, let's just catalog some properties of covariance. And these properties of covariance turn out to also be properties of variance because there's a very close relationship between variance and covariance, as we'll see. So I'm going to write these down. I'm not going to prove them necessarily, but they're good to have handy in case we need them. First is to realize that first property of variance is called symmetry, which is just covariance of x and y is equal to the covariance of y and x. This is not a directional relationship. Just realizing the definition here of covariance. A lot of these properties we can actually see by just looking at, we just look at this definition. So let me copy this down for us. Oops. Okay. So multiplication is commutative. So if we had x on the left, y on the right, it's the same as having x on the right and y on the left. Scale and location. So we saw this last time for variance. How does it work for covariance? Covariance of ax plus b with y works much the same way. Covariance is unaffected by changes in scale, and we pull the scalar out, but we only get one of them. Remember, for variance, we get two of them, and that's kind of curious, is that we get alpha a squared times the variance of x. Here we just get a times the covariance. And that's because, in general, there's what's called, well, we'll see why in a second. First, I have to talk about additivity. If we have two random variables, so if we have covariance of x plus y with z, we have covariance of x. It's equal to covariance of x with z plus covariance of y with z. And these properties together come together to give us what's called bilinearity. So scale and location with additivity gives us this property called bilinearity, which is if we have a linear combination of random variables on the left and a linear combination of random variables on the right, we just get the whole thing to come out as a sum, so we can break it down into sum over I, sum over j. For each term, we pull out the constant ai for the left, bj for the right, and we get the covariance of xi with xj. And so the last thing to observe here is in terms of the relationship to the variance, which is just that the variance of x is equal to the covariance of x with x. You can see that by looking up here, right? The definition of variance is the expectation of x minus the mean squared. Well, if x is here and here, we have x minus mu, that's just the square, right? So that's the same. And so this is where we can see that, okay, how do we rederive the variance of ax plus b? Well, it's the covariance of ax plus b with ax plus b, which according to this here is we get, first of all, we don't care about the b's. We get the a here, a is here and a is here, so they come out as a pair, a times a times the covariance of x with x, which is, of course, a squared times the variance of x. Okay. So those are some properties of covariance. We'll revisit these later on as they become more and more relevant throughout the course.